Hi, and welcome to this video. We're going to cover a statistics question as requested on Wyzant, and it's about normal distribution, as you can see, where it talks about the distribution being bell-shaped. So we're going to give it that name, of course, and there's other pieces to this question that I'm bringing up as it relates to solving it. And I would think that the main way of solving it is empirical rule, which we'll see in a moment how that is. But you could also solve it by using the standard score, which we refer to it or denote it as the letter Z. So I'm just going to add that to the title up here. Okay. So let's read the question and talk about how we break this down and figure out the approach to solving it. So it reads, scores of an IQ test have a bell-shaped distribution with a mean of 100 and a standard deviation of 20. And that's not too far off from what it actually is. It's probably the exact numbers or what is the average of those values usually. What percentage of people has an IQ score between 40 and 160? Now, these people, we don't know of what country, nationality, that we're talking about. So we're just going to assume we're talking about the United States, But of a particular population, they want us to find, given the mean and standard deviation, what is the percentage, what is the other words are proportion, probability that a certain number of people fall within the scores 40 to 160 on the IQ test. Okay, so we got the values, we got the information here, which is really all that we need in order to do all that we need to do. And again, we can use the empirical rules. So just a little reminder on what that is. The empirical rule is a set of percentages, middle percentages that relate to a specific range of values. And in this case, we're going to call these values X variable, X values, because that tends to be the letter that we use to represent that variable or random variable. And so these areas under the curve represent those specific ranges that's pretty consistent for any set of data that is considered normalized or has a normal distribution. So that's why you see in the title above, all three of those concepts directly relate to each other. Okay, so the empirical rule has 68% for the -1, +1, or left to right, or let me put it like this, one standard deviation to the left and to the right of the mean. You have 95% representing two standard deviations to the left and right of the mean, and then finally 99.7% to three to the left and right of the mean. So I'm trying to not stumble through that, but there it is. Okay, so the total area, always remember the total area under the curve, and I like to say from tail to tail, is 100%. Once you go past the tails and virtually past 3.5 on that X value or axis, you're pretty much getting close to zero, close to the axis itself, okay? Because this is a continuous curve, right? And it's all based on calculus. So there's actually calculus statistics where you can look into that background on how they even produce these type of graphs and procedures in order to do the calculations we do in a lot of different statistics courses. Now, oftentimes this type of question will just stay here because they're giving you specific values, and it's sometimes the way in which they ask the question, information they give, the fact that it's bell-shaped. Most people then immediately think empirical rule, and then they want to know the percentage between two values. And these two values are at equal distance from the mean. Okay, and we'll work on that and see what that looks like. But besides the empirical rule, we can use the standard score. And that makes now the normal distribution the standard normal distribution. So we just throw that standard in front, and now we're working specifically with those values from -3 to +3, or from like -3.49 to +3.49. Okay, so depending on what your charts look like, and I may need to bring that up in this video, but we're going to just probably focus on this because that may be where you are in your course. If you're watching this video and this is a question that you have, but sometimes you may also have in your course covered standard score right beside empirical rule to show how they're directly related to each other. And even you can even see that it's like a direct offshoot from the empirical rule. Notice it's -3, -2, -1. Then you have the mean, which in standard normal distribution, every mean that's converted into a z-score is going to be 0, representing halfway or 50% of the curve. And then you go +1, 2, 3. So it's literally the same thing. Literally the same thing. So the only difference is what are those values on the axis, right? So let's just use the empirical rule mostly to answer the question, but just know you can also use the standard score, and we'll see what that looks like as well. At this point, though, if you want to just run with the empirical rule to help answer it, then you can stop in this video when we finish that part. But if you're interested or if you have been covering the standard score, please continue on through this video so you can see what it looks like as it relates to this problem and how we get the same exact answer regardless of which path you take, because it's the same thing, okay? So with the empirical rule, as you've probably seen in practice and lectures, you simply take the information that you're given and apply it to the situation or the how do I say this, the structuring of the normal distribution curve and the axis related to the empirical rule. Notice it's 1, 2, and 3 standard deviations out from the mean. So of course we're going to start with what's the mean, which again is 100. And we're going to fill in the rest of this axis by simply adding 20 and subtracting 20 from the mean. So when we add 20 one time, we get 120 at +1 standard deviation. And notice I'm using the Greek symbol sigma, which tends to be used for when we talk about population standard deviation. I'm going to assume this is a population set of information or a population set. All right, when we add another 20, that takes us to 2 standard deviations, right? So you can look at this as +20 and then another +20, or to go from the mean to 2 standard deviations, we do 2 times 20. So both of those play out the same way. And then when you add one more 20, you get to 3 standard deviations. Notice that's the value, the upper bound of the range that we're being asked to find the percentage of, okay? And then when we move to the left, when we subtract 20, we're going to get 80. I almost said 1. We're going to get 80. Then we subtract another 20. We get 60. And one more, we get 40. Okay, so that was literally going in the negative direction with the standard deviation. And remember, the standard deviation is literally showing the spread of the data, right? Roughly based on the mean. So the mean and standard deviation are partners when we talk about the normal distribution, or just about any distribution, but most definitely normal distribution. So now that we have that in place, we can use the same percentages, right, dealing with the empirical rule. So we have 68%, and I'm just making sure my colors stay consistent, 95%, and finally 99.7. And again, what is our range here that they asked for? We're looking at 40 to 160. So this is how most, if not all the time, you will see it written when you're dealing with random variables or X variables like this. P of 40 to 160. And it's written in inequality form or notation. So we're showing that range where the lowest boundary is 40 and the upper is 160. So with the empirical rule, we see that the area related to that range is simply 99.7%. And that's our answer. That's it, right? So the empirical rule can be quick and easy like that when you are just simply dealing with in between, okay? And so because these two values were equally distant from the mean, exactly 3 standard deviations from the mean, then we can just use the empirical rule, right? But let's say you wanted to use the standard score, right? So you would use this formula right here, And we're going to just give some notation here. So x1 is the lower bound, which is 40. x2 is the upper bound, 160. And so we're simply going from x to z, and we're going to use the standard score to find our probability through the way of finding the area of z scoring or standard scoring. Okay, so oftentimes you're going to use a chart, and bearing with me in this video, I will just bring that chart up, and hopefully it doesn't take too much time. But you can also use your calculator. You can also use other statistical software to find those areas. Excel, I believe, has a function like that. And of course, you have your StatCrunch if you're using, say, what is it called? Pearson. Okay, if you're using Pearson, MyLab Math, then you can definitely use that. JMB, I don't know why I'm forgetting. That's another one. RStudio. So there's a ton of different statistical software out there. SPSS is definitely another one. Okay, so we are in this formula sheet that I have from a textbook that I used as a embedded tutor. Okay, and this is the chart, one of the many charts that you'll definitely see, if not use, in statistics. And so we have the Z column and row, first column, first row, and you simply bring those two types of values together. So let's say we have there negative 3.40. You would simply just add the two, and that's your z-score. Okay, so that's essentially how you would read it, and where they cross is the area related to that z-score. That's how a lot of these z-tables are essentially set up. Not all of them look like this, though. I've seen others where they look more like the t-distribution, which I more or less like that chart. I like how that chart works. All right, because it's just a little bit more straightforward. But anyways, so let's see what we get here. So we're going to convert from the x values to the z score. All right, and then we're going to use the z score to find the probabilities. And so if we were to follow through with how that setup looks like, just really quickly, what we're essentially doing is we're finding the z score, and then we're going to use the probability up to those z scores. Okay, so we're going to subtract the smaller area for the smaller boundary from the larger area of the larger boundary. Okay, so this is just one part of the setup, but when we find the z-scores, it's going to look something like this. Let me label them. P of z1, and then whatever that z-score is. All right, we already actually know what they are. If you're paying attention to what I was covering earlier, the standard normal distribution is exactly like the empirical rule as far as the counting of the standard deviations. And z-score is simply the measure of position. So that measure of position directly relates to the spreading of the data through the standard deviation. Okay, so let me go back here and calculate. So we have here 40 minus 100, right? And that's going to be negative 60 divided by 20. And that's simply negative 6 divided by 2, right? If you just cancel out the 10, the power of 10, we're left with negative 6 over 2, which is negative 3 there. For Z2, we have 160 minus 100, which is 60 over 20, or 6 minus 2, which gives us positive 3. So there it is right there, plain as day. It's the same 3 that we see here in the empirical rule, the negative 3 standard deviations and positive 3 standard deviations, right? So again, we know the answer, but let's just work through it and see what we get. So we have there the z-score, and that should be positive 3, not negative 3. So the z-score of the upper boundary, it's 3, and then the z-score for the lower boundary is negative 3. So all we've done there is simply changed what the value looks like to set it with that particular distribution, the standard normal distribution. And so now we're going to find that area. Now, since I'm on the left side, because it's all negative z-scores, I'm going ahead and just finding that. So I'm here and just finding that area. So we see there's negative 3.00 to make it negative 3 simply. And the area is 0.0013. So that's the area going up to the value of negative 3. If we go to here, right, we're essentially talking about the area literally going up to that boundary. That's what that means. Okay. And so we found there to be the approximated, because those values on that chart are approximated values, 0.0013. Okay. So now we're going to go to the right side and we're going to look for 3.0. So way down here. And you notice that the 00 for the hundreds place is that next column over. So where they cross here, whoops, where they cross here, we get 0.9987. 0.9987. So on our chart here, what we're essentially doing is we've gotten that area going up to 3. I went over a little bit, but don't worry about that. All right. And so when we subtract those two areas, we're getting that middle that we've already seen in the empirical rule. So we've just proven in this video how the two are directly related to each other, right? And even how maybe one comes from the other, right? So that middle 99.7 is our answer. Right? So something like that, if you want to go to Desmos and just double check, so 0.9987 minus 0.0013. So we get 0.9974. Okay, so it's just a little bit more precise there, but let's just round it out to those 3 decimal places and we get the 0.997 or 99.7%. And you would definitely provide the answer in percentage because they ask for the percentage, not just simply the proportion or probability. So make sure you do convert into percent, regardless of how you do your work here. But yeah, that is the 2 different ways to find the same answer. And we show again, the fact that they're literally linked. They're literally the same. It's just different ways of looking at the information. All right, I hope you found this information, this video helpful, and definitely let us know if you have any other questions. See you next time.